Mathematical induction is, we talk about it in this section because math induction is often used to prove conjectures having to do with sequences and series, and that's what we're studying in this chapter. All right, math induction involves two steps. Here are the two steps. To prove that a proposition is true for n items, we need to show first that the proposition is true for n being 1 for the first item. And then, and here's the kicker, we need to show that the truth of the proposition for k items implies the truth of the proposition for k plus 1 items. That is, the truth of the kth item implies the truth of the k plus 1th item. Now, this situation, these two ideas together, creates a kind of a domino effect in this situation. If we show that the proposition is true for the very first item, then that kind of kickstarts the whole notion. But then when we say that the truth of the kth item implies the truth of the k plus 1th item very generally for any k and k plus 1th combination in the entire group of this infinitude of propositions, then isn't it true that the truth of the first item implies the truth of the second item, and the truth of the second item implies the truth of the third, and the truth of the third implies the truth of the fourth, and so forth? Why, with this idea that the truth of the kth item implies the truth of the k plus 1th item. Let's use math induction to prove this conjecture. It says that the sum of n items given by 1 plus 2 plus 3 plus 4 and so on through the nth item is equal to the expression n times n plus 1 over 2. Is that true? Well, let's see what this means. If we're talking about adding 4 items, 1 plus 2 plus 3 plus 4, that would be 4 and 3, 7 and 2, 9 and 1, 10. So that sum would be 10. Does it meet the form over here if n is 4? Well, this would be 4 times 4 plus 1 over 2. 4 times 5 is 20, 20 over 2, 10. So it certainly works when n is 4. Now, by math induction, here's what we need to do. We need to show that the conjecture is true when n is 1. So when we're adding just one item, the sum of one item would be 1. Now, does it meet the form that we have over there? Well, that would be 1 times 1 plus 1 over 2. Well, this is 2 over 2 or 1, so it certainly works in that case. Now, we then assume the truth that the sum of k items meets the pattern that we talk about, that we have in the conjecture. But does that imply the truth for the k plus 1th item? That is it therefore the truth that the sum of k plus 1 items given by all of these plus the next item, you see, equal to this expression for the k plus 1th item? Now, here's where we have to think about how to write this and where this comes from. This is the k plus 1th expression, and just replace this k with k plus 1, replace that with k plus 1, you see, and we get this. Okay, so that's the idea. Now, in order to show this, the strategy generally is to write this and show that, and then make a replacement, refer back to something that you made in this assumption. All right, and then we want to lead to this expression. So that's the idea. So we start with the sum of k plus 1 terms would be 1 plus and so on all the way to adding the k plus 1th item. All right, and then we utilize this information and then try to show that. All right, here's what we're doing. We take s of k, all right, here's s of k. Now s of k plus 1 means just tack on the k plus 1th item. That's what this is. All right, now, here's where we jumpstart the whole thing. We take this part of it right here, and we replace with that. You see that expression. Okay, so that's what comes down to right here and replaces this. And now we still have the k plus 1th item being added. Now we want to manipulate this expression into the form that we want it. Then that form was k plus 1 times k plus 2 over 2. Okay, let's see if we can do that. We see that in these two terms, k plus 1 is a common factor. So we pull out k plus 1 as a common factor. When we pull k plus 1 out of this term, we're left with k over 2. When we pull k plus 1 out of this term, we're left with 1. Now, what about this? What's this? Well, let's see. We have a fraction here. We need common denominators. 1 can be thought of as 2 over 2. So when we write 1 as 2 over 2, we have k plus 2 over the common denominator of 2. So this becomes that. And now we can rearrange factors a little bit and write this as k plus 1 times k plus 2 over 2, which is what we need to do.
We're going to use mathematical induction to prove that the formula is true for all natural numbers n. 2 plus 4 plus 6 plus ... plus 2n equals n times n plus 1. So we're going to let p of n denote this statement. Here. And then step 1, p of 1 is the statement that 2 equals 1 times 1 plus 1, which is true. Step 2, is assume that p of k is true. That is 2 plus 4 plus 6 plus ... plus 2k equals k times k plus 1. We want to use this to show that p times k plus 1 is true. Now, two plus 4 plus 6 plus ... plus 2k plus 2 times k plus 1 equals k times k plus 1 plus 2k plus 1, which equals k plus 1 times k plus 2, which equals k plus 1 times k plus 1 plus 1. Thus, p times k plus 1 follows from p of k. So by the principle of mathematical induction, P of n is true for all n. We need to show that use mathematical induction to prove that the formula is true for all natural numbers n. 5 plus 8 plus 11 plus plus 3n plus 2 equals n times 3n plus 7 over 2. So we're going to let P of n denote this statement. So step 1, we need to show that P of 1 is true, and P of 1 says that 5 is equal to 1 times 3 times 1 plus 7 divided by 2, which is true. So step 2. We assume that P of k is true, and P of k is this statement once again, but instead of n, we're redefining this with k in place of n. And we want to use this statement to show that P of k plus 1 is true. So once again, we're assuming this is true. This is part of step 2. But we're substituting k in for n. And we're going to use this to show P times k plus 1 is true. So now, five plus 8 plus 11 plus plus 3k plus 2 plus 3 times k plus 1 plus 2 equals k times 3k plus 7 over 2 plus 3k plus 5. So this is the induction hypothesis. And this is equal to 3k squared plus 7k over 2 plus 6k plus 10 over 2, which equals 3k squared plus 13k plus 10 over 2, which equals 3k plus 10 times k plus 1 over 2, which equals k plus 1 times 3 times k plus 1 plus 7 over 2. Thus, p times k plus 1 follows from p of k. So by the principle of mathematical induction, p of n is true for all n. Plus 2. Use mathematical induction to prove that the formula is true for all natural numbers n. 1 times 2 plus 2 times 3 plus 3 times 4 plus plus n times n plus 1 equals n times n plus 1 times n plus 2 divided by 3. So first we'll let p of n denote this statement. And step 1, p of 1 is the statement that 1 times 2 equals 1 times 1 plus 1 times 1 plus 2 divided by 3, which is true. Step 2. We assume that p of k is true. And we're redefining, or we're using p of k is equal to this statement, but instead of n, we're substituting k in. And we want to use this statement to prove that p times, or p of k plus 1 rather, is true. Now, 1 times 2 plus 2 times 3 plus 3 times 4 plus plus k times k plus 1 plus k plus 1 times k plus 1 plus 1 is equal to k times k plus 1 times k plus 2 divided by 3. plus k plus 1 times k plus 2, which is equal to k times k plus 1 times k plus 2 over 3 plus 3 times k plus 1 times k plus 2 over 3, which equals k plus 1 times k plus 2 times k plus 3 over 3. Thus, P of k plus 1 follows from P of k. So by the principle of mathematical induction, P of n is true for all n.